This is a really important day. We discuss L'Hopital's rule, which is something you can use sometimes to evaluate limits. And it's important to understand, as we will discuss today, when you can use L'Hopital, and we will practice using it, but also when L'Hopital does not apply, because it's not the case that we may use it every single time we want to calculate a limit. So here are two examples that motivate the need for or the desire for L'Hopital, and that's these two. The limit as x goes to infinity of e to the x over x, and the limit as x approaches 1 of natural log x divided by x minus 1. Well, if we just think about what's happening, so let's think here. Here, what's happening? E to the x, as x approaches infinity, and as similarly as x approaches infinity, x itself, well, is going to infinity. So here we get this infinity over infinity, okay? Now if we move to this one and we think about what's happening, well, natural log is continuous. As x approaches 1, natural log x approaches ln 1, which is 0. So we get 0. And then in the denominator, as x approaches 1, x minus 1 approaches 1 minus 1, which is 0. Okay? And these are both what's called indeterminate forms. And when you get this, when you think about what's happening or you try to evaluate a limit, it doesn't mean the limit does not exist. It doesn't mean the limit exists. What it means, and we talked about this even in our limits day a while ago, is that you must do something, right? And typically the something, maybe I will just remind you briefly, when have we seen something like this before? If we were looking at the limit as x approaches 2 of x squared minus 4 over x minus 2. This is an example where we saw an indeterminate form before. Here we try to evaluate, we get 0 over 0. And what we did in this example is we just factor and cancel. Well, this way we get the limit as x approaches 2 of x plus 2, and this is 2 plus 2, which is 4. So this was an example where here we got an indeterminate form, and I would put this in quotes. I'll put it in quotes here too. And it is a signal to us that we must do something. Maybe I'll just say recall here, because this would be something that we could have done much earlier in the semester. Okay? But if you take this approach here or here, I don't really see any algebra that we can do to help us evaluate this limit, or I don't see any algebra we can do here to help us evaluate this limit. There's not a simple factor and cancel type approach here, okay? This is when L'Hopital comes into play. So let's talk about the setup for L'Hopital, and then we will come back to these two examples. Suppose f of x and g of x are differentiable and either, well, there's two possibilities. The first one is that the limit as x approaches c of f of x is plus or minus infinity, and the limit as x approaches c of g of x is plus or minus infinity. This is one possibility. And the second one is that the limit as x approaches c of f of x is 0, and the limit as x approaches c of g of x is 0. In both of these, c might be a finite number, like here, c is 1. C could also be infinity, okay, just as a comment. But then the statement is, if you want the limit as x approaches c of f of x divided by g of x, well, this would be the limit as x approaches c of f prime of x divided by g prime of x. And this is provided g prime is not equal to 0, right around x equals c. But let's talk about this for a second, because as I mentioned at the start, it is quite important to know when you can use L'Hopital and when you can't. So what do we need here? Well, we absolutely must have one of these two conditions. Namely, if you look here, you're trying to take the limit of a quotient, f divided by g. And when you try to evaluate, well, if you're in this first condition, we get plus or minus infinity over plus or minus infinity. That's like this, okay? Or in the second, we get 0 over 0. Then what we may do is we take the derivative on the top, take the derivative on the bottom, reevaluate the limit, okay? Now this is not a quotient rule. This is you take the derivative just of the top function, take the derivative of the bottom function, that's here, and then evaluate the limit again. And if you do this, and let's say you get another 0 over 0, or another plus or minus infinity over plus or minus infinity, then you could, for example, use L'Hopital a second time. Let's see, let's do these two using L'Hopital, because we are in the case that we have this indeterminate form and indeterminate form. So let's do these two before we move on to some other examples. For this first example, e to the x over x, we've already thought about the fact that we do get an indeterminate form, so we may use L'Hopital. Now you need to, in your work, you need to say that you're using L'Hopital so that whoever is grading your work knows, okay? You can either, I'll show you maybe two different ways in these two different examples. We can either, well, let's take the derivative on the top, take the derivative on the bottom, okay? Now we reevaluate. So I can write here by L'Hopital, this is one way to show your work, is just to write it. Now, if I reevaluate the limit, now I have just e to the x, and e to the x approaches infinity. This grows without bound. So this answer would either be infinity or does not exist as a finite number. Okay? Now let's do the second one, the limit as x approaches 1, natural log x over x minus 1. Okay? Again, we've already verified we get an indeterminate form. We have 0 over 0. Let's take the derivative on the top, take the derivative on the bottom, reevaluate the limit. Okay, derivative of natural log is 1 over x. The derivative here is 1 minus 0, which is just 1. Now we're looking at a limit as x approaches 1 of 1 over x. This is just 1 over 1, which is 1. Now, I'll show you the other way that you could illustrate that you've used L'Hopital. I have seen like this. You put an LH on top of the equal sign where you have used L'Hopital. You see, this step from here to here was L'Hopital's rule. Okay, so this limit exists, and it is 1. Now let's do some more examples. For the first one, the limit as t approaches 0 of e to the t minus 1 over t cubed. Well, let's try to think about what's happening. We must actually check that we get an indeterminate form before we just jump in and start using L'Hopital's rule. So here you see we get e to the 0 is 1, so we have 1 minus 1, which is 0 over 0. Okay, so we do have an indeterminate form. We may use L'Hopital's rule. I'll write it up here. And then it says take the derivative on the top, take the derivative on the bottom. We get e to the t divided by 3t squared. Now, don't just immediately start using L'Hopital again, because what's happening here? Well, as you approach 0, e to the t approaches e to the 0, which is 1. So my numerator is approaching 1. My denominator is going to 0. This is approaching infinity, or does not exist. Okay? Now this one, we want the limit as x goes to infinity, log base 2 of x divided by x squared. The log base 2 of x. Well, this function grows without bound. And similarly, x squared grows without bound as x, well, goes to infinity. So here we do get an indeterminate form. This means we may use L'Hopital. This would be the limit as x approaches infinity. We want to take the derivative on the top, take the derivative on the bottom, reevaluate the limit. Here, this is 1 over ln 2 times x. This is the derivative of log base 2. And then we get divided by 2x. Now, this is really fraction over fraction. Here is where I use L'Hopital. I don't need to use L'Hopital again. I can work with, well, I can just invert multiply, and I will get a sense of what this is. This, if you invert multiply, the 2x is really in the denominator. So this is 1 over 2 ln 2 times x squared. Maybe I'll put parentheses like this. Now you see what's happening. Fixed numerator, denominator is growing without bound. This limit is 0. Okay? Here are 2 examples, and I will just preface this by saying we can use L'Hopital on both of these, but let's figure out why. We have the limit as theta approaches pi, sine 5 theta divided by theta minus pi. What's happening with the numerator? Sine is continuous. As theta approaches pi, this approaches the sine of 5 pi, which is 0. And then the denominator is approaching pi minus pi, which is 0. And so we can use L'Hopital. We take a limit as theta approaches pi. We take the derivative on the top. This is chain rule. Cosine 5 theta times 5, which is the derivative of the inside function. And then the derivative on the bottom is 1. And, well, I have differentiated with respect to theta here. Now I can just compute. This is just 5 cosine 5 theta, continuous function. So the limit will be equal to 5 cosine of 5 pi using continuity. And if we think here, this is here. Well, we will go around 2 pi, 4 pi, and then out here, again, 5 pi is here. The cosine is minus 1, so this limit is minus 5. Now, this example, we have 2 to the t minus 4 to the t divided by t. We want the limit as t approaches 0. The numerator, well, 2 to the 0 and 4 to the 0 are both 1. So we get 0 and then over 0. This means we may use L'Hopital. Okay, so this is a limit as t approaches 0. The derivative on the top would be ln 2 times 2 to the t minus ln 4 times 4 to the t, and then the derivative on the bottom is just 1. Now we can evaluate. This limit is just ln 2 times 2 to the 0 minus ln 4 times 4 to the 0. But 2 to the 0 and 4 to the 0 are 1. This limit is natural log 2 minus natural log 4. Okay? So both these limits exist. Great. My next two examples, if you look at them, you may not see L'Hopital, and even for one of them, I will not use L'Hopital. We don't always when we evaluate limits. But this first one, first of all, let me just make a comment. This is a one-sided limit. This is a limit from the right, and it must be because the natural log is not defined for negative values. It's also not defined at 0, so we really wouldn't talk about a two-sided limit at 0. But we can use L'Hopital for one-sided limits. This is not a problem. But what appears to be a problem here is we don't have a quotient. We have a product. If we think about what's happening, natural log, well, it kind of looks like this. This is more or less the shape. And we see as you approach 0 from the right, natural log approaches minus infinity and t squared approaches 0. Okay, so it's not exactly the right form to just jump into L'Hopital, but we can use some algebra first. I'll put that in a box maybe. This would be a limit as t approaches 0 on the right. I'll put the ln t in the numerator, and then I will move the t squared into the denominator like this. You see, these two are equal using, say, properties of exponents. But now I am looking at a quotient, and if I think about what's happening as I approach 0, now my numerator is approaching minus infinity, and the denominator, well, as t approaches 0, 1 over t squared is approaching infinity because we have 1 in the numerator and the denominator is going to 0. So we have infinity over infinity. Now we are in great shape for L'Hopital. Okay, so this equals, and this is by L'Hopital. We have a limit as t approaches 0 on the right. Take the derivative on the top. Take the derivative on the bottom. Where the denominator is here is t to the minus 2. So when I differentiate, I get minus 2t to the minus 3, which we see here, okay? Now looking at this, what I want to do now, properties of exponents. So this is a limit as t approaches 0 on this side. We invert and multiply. This is minus t cubed over 2. And here is the property of exponent part. We get minus t squared over 2. When we evaluate this limit, we get, well, minus 0 over 2, which is just 0. Okay? So you notice I had several steps to calculate this limit. Most of it was algebra, but only this step here was L'Hopital's rule. Now for this one, maybe before we begin, let me sketch both of these basic shapes, we see an e to the x and an e to the minus x. Okay, e to the x, like this, exponential growth. This is the basic shape. E to the minus x, exponential decay. This is the basic shape. If we just think about what's happening, and you see this is a limit as x approaches minus infinity, well, this part, e to the x, maybe I should label. E to the x going in this direction, this is where we're looking, this way and this way. E to the x approaches 0. E to the minus x approaches infinity. So here, this would be approaching, well, this numerator growing without bound. Denominator is going to 0. Well, if you think about it, growing without bound divided by going to 0, this will go to infinity, just thinking. And it's not L'Hopital. So this is not L'Hopital because we do not get indeterminate form. It is not of the form 0 over 0 or infinity over infinity. So I'll just say do not use L'Hopital. As I mentioned at the beginning, we don't always use it, and we will see some more where we don't. What I would probably do, or what could help you, if you have a hard time thinking about this one as I was just discussing it, is you can break this into a sum and see it a little bit easier. E to the x over e to the x is 1. And then e to the minus x over e to the x would be e to the minus x, which is minus 2x. And now this is a little bit easier to think about. This is just a fixed number, 1. There's no x in it. And this term, it is a situation like this. E to the minus 2x is exponential decay. So as you go to minus infinity, this term is growing without bound. And so we get infinity or does not exist. Okay? Here's my next example, and I give myself a little more space. This problem comes off an old final exam. It's quite fun, but we will see there are multiple steps. Well, first of all, ask yourself, can we use L'Hopital? So what's happening here? My numerator, as x approaches 0, we get ln1 minus 0, and then the denominator is like this. ln1 is 0, so we do in fact get this indeterminate form. We may use L'Hopital. This is a limit as x approaches 0. We take the derivative on the numerator, take the derivative of the denominator. Well, the numerator, let's look at this first term. This is chain rule, where the inside function is x squared plus 1. When we go to differentiate, we get like this. Derivative of the outside is 1 over x, evaluated at the inside, and then times the derivative of the inside function. And then we subtract the derivative of x squared, and this is all over 4x cubed. Now, if you think about this, we still get 0 here, 0 here, 0 here. So we're not ready to evaluate just yet. What I personally would do is let's get a common denominator in the numerator and try to make this into just one fraction. It'll be easier to realize what's going on. So what's happening, this 4x cubed is really in the denominator. And then I will have x squared plus 1 as my common denominator in the numerator. This will be 2x and then minus 2x times x squared plus 1, okay? Now, let me just multiply everything out. Then I'll have polynomial divided by polynomial, which will be easier to work with when I think about this limit. My numerator, look, I have a 2x minus 2x. Those add to 0. And so I have one term. It's negative 2x cubed. And then my denominator has 4x to the 5th power plus 4x cubed. Okay? Now, technically, I have 0 over 0 again, but if I have polynomial divided by polynomial, I'm not going to use L'Hopital, okay? We saw this on our limits day, especially with limits at infinity, and this is a limit at 0, not infinity, but when we had polynomial divided by polynomial, we would divide by a power of x. And that's much simpler. And even now, knowing L'Hopital, if I had a limit at infinity, or at 0 in this case, and I have polynomial divided by polynomial, I will not use L'Hopital. I will still make it easier on myself and divide by a power of x. So let's do this here. Well, I will divide by the power that is common to all of these, which is x cubed. So this is a limit as x approaches 0 of negative 2 over, we have 4x squared plus 4. Now you see, this I'm ready to evaluate because this goes to 0. Maybe I'll circle it. This part goes to 0, and so I am left with negative 2 over 4. This limit is negative 1/2. Okay, it took a number of steps, but it's a great exercise. Now, before I erase, because I was about to erase and move on to the next one, and I realized I didn't put where I used L'Hopital. So we only use L'Hopital at one place, right here. So this is where we use L'Hopital. And this is the only place that I use L'Hopital's rule, was right here on this equal. You see, take the derivative of the top, take the derivative of the bottom. Everything else was just algebra. This is a great problem because we really have to think about the trig functions here. So we want a limit as theta approaches minus pi over 2 of 3 plus 3 sine theta divided by 1 plus 2 cosine theta. So let me think about the unit circle here. Minus pi over 2 is here. And the point on the unit circle is 0 minus 1. Okay? So the sign of minus pi over 2 is negative 1. The numerator is approaching 0. And the denominator is approaching, well, 2 times negative pi over 2 is negative pi. And here is where negative pi is. Negative pi, where the cosine is minus 1. Okay, so the denominator is approaching 1 minus 1, which is also 0. We may use L'Hopital. Okay, so this would be a limit as theta approaches negative pi over 2. Take the derivative on the top and take the derivative on the bottom. Okay, so far so good. Well, if we look at this, what is happening as theta approaches minus pi over 2? Look, the numerator, cosine of minus pi over 2 is 0. Maybe I'll do the second step as brown. So this is approaching 0. And out here, this would be sine of minus pi. Out here is 0. we have another indeterminate form. Now, this one is quite cool. I see two options. One, use L'Hopital a second time. And maybe I will show that. But option two would be to use a trig identity. So let's first use a trig identity. This would be 3 cosine theta divided by minus 2. The sine of 2 theta, you might remember, this is 2 sine theta cosine theta. And then the cosines can cancel. We get a limit as theta approaches negative pi over 2 of 3 over negative 4 sine theta. And the sine of minus pi over 2 is minus 1. So when we evaluate this limit, we get positive 3 over 4, okay? Now in this first part, let me put a line, and maybe I will talk about using L'Hopital a second time. We should get the same answer of 3 over 4. So here is, maybe I'll put this way number 1 here. And then I will do way number 2 here. And when I continue here, I am continuing from this part. Okay, we got 0 over 0 after our first evaluation of L'Hopital, okay? So way number 1, as I mentioned, and I'll write this was a trig identity to help us. And way number 2, I will just use L'Hopital again because I have an indeterminate form, 0 over 0. So let's do that here. Well, this would be a limit, and this is L'Hopital. As theta approaches minus pi over 2, take the derivative on the top, minus 3, sine of theta, and then take the derivative on the bottom. We get minus 4 cosine of 2 theta. Right? So far, so good. Sine of minus pi over 2 is negative 1. Cosine, this would be cosine of minus pi, which is also negative 1. And you see, well, we have 1, 2, 3, 4 minus signs. It's positive 3 over 4. Okay? So both of these, I did it 2 ways just to illustrate that we did have more than one possibility, but both of them began, we did one L'Hopital, okay? Then we broke from this equals, we broke into 2 possible second steps. Trig identity, and then L'Hopital second time. And, well, as we should, same answer using both techniques. 2 more. But first step, just as we have done, we must check, can we use L'Hopital or not? Let's look at this first one. What's happening as we approach 0? The numerator is approaching 0 times 1, which is 0. And the denominator is approaching cosine of 0, which is 1. Okay? Well, this is not indeterminate, so we do not use L'Hopital here. Because we do not have an indeterminate form, this answer is just 0 over 1, which is 0. Okay? Now, this one, it's the tan inverse of x divided by 3x. And we want to limit as x approaches 0. Well, tan inverse, as you know, hopefully you know, is my favorite of the inverse trig functions. And the basic shape is like this. Well, the tan inverse of 0 is 0. So here, this in the numerator, because tan inverse is continuous, is approaching 0. and the denominator is approaching 0. So in fact, we do have an indeterminate form. We may use L'Hopital, where we take the derivative on the top, derivative at the bottom, reevaluate the limit. The derivative of tan inverse is 1 over 1 plus x squared. The derivative of the denominator is 3. And then if we just this is really sitting in the denominator here, we get like this, 3, 1 plus x squared. Now we can evaluate this at 0. We get 1/3. So this limit is 1/3.